All right, guys, and this is going to be probably a short video just on drag forces. We're not going to go into a tremendous amount of detail on this. Um, but drag forces, first of all, this is a term that's used, I think I mentioned this before, but for any resistive force, so any force that resists motion, resistive force due to a fluid. Due to fluid. And a fluid could be a gas like air, or it could be a liquid like water. But we're going to specifically think about air resistance as maybe the most kind of common example, at least in everyday life. And there's something very interesting about air resistance, or in drag forces in general, which is different from the other forces that we've talked about, in that they're variable, and it's kind of hard mathematically to deal with the fact that they change, that they're variable. And that's why we aren't going to go into an enormous amount of detail. If you take more advanced physics courses, you will learn how to deal with this in a more rigorous mathematical way. But I just want to point out right now that air resistance depends, or maybe I'll start by saying the magnitude of the force depends on the object's speed. What do I mean by that? Well, if you think about this carefully, it might be fairly obvious that if I imagine, let's say, here's a road right here, and I've got a car driving down the road. Here's this car. As the car moves, so let's imagine that it's going in this direction. As the car moves, it's going to encounter all of these little air molecules, right? Now, each of these little red dots you can imagine is an air molecule. So it's going to encounter all of these air molecules, and the car has to push those air molecules out of the way, right? The car has to, on each of these little air molecules, right? Each one, the car's got to push it out of the way, push it out of the way, push it out of the way, push it out of the way. And of course, by Newton's third law, if the car pushes the air molecules out of the way, then the reaction to that is that the air molecules are going to push ever so slightly back on the car. This is the action-reaction principle. Car pushes on the air molecules push back on the car. So that's really where it's coming from. Now, if the car is moving slowly, then per unit time, the amount of air molecules, the number of air molecules that the car has to push out of the way is fairly small. But as the car goes faster and faster and faster, you can probably see it's going to plow through more air molecules. And so as it goes faster, it pushes on more air molecules, and therefore more air molecules push back on it, which is sort of a long descriptive way of saying that as the velocity goes up, the drag force also goes up. And that's interesting, and we're not going to deal with it in a rigorous mathematical way, but I just want to kind of give an example, maybe an example of a dropped object. So let's imagine here that I take here's a rock, and I drop it, and maybe we could just come up with some values. We could say that the mass of the rock is 2 kilograms, and I'll use G equals 10. We know G is 9.8, but I'm just going to use 10 just to make the math easy here. And I'm going to say that this rock, I drop it, so the initial velocity is 0. And so at this point in time, if we were to think about the forces, since the velocity is 0, then the drag force is also 0, because the rock isn't pushing on any air molecules, so the air molecules aren't pushing back on it. So if I were to draw the forces at this moment, it would just be the force of gravity, and we would see then that the acceleration then is simply going to be 10, or 9.8, but I'm using 10. You could imagine some later time here where, you know, the rock is fallen for a period of time or it's accelerated for a period of time. So now that there is a drag force. So maybe I'll just say we've got the gravitational force down, and now we do in fact have a drag force. I'll write FD for drag. And maybe I'll just, rather than calculating it directly, I'm just going to tell you that this particular drag force is 10 newtons at this moment of time. And now if we wanted to find the acceleration, I'd have to use F net equals ma. The net force would be mg, That's 2 times 10, or 20. Right? This is going to be equal to 20 newtons. That's 2 times 10. 20 minus 10 equals 2 times A. So we get A is 5 meters per second squared. So the acceleration is now only 5 meters per second squared. Now to be clear here, the object is not slowing down. When I say that the acceleration here has gone from 10 to 5, that doesn't mean it's slowing down. It means that it's still speeding up, but it's speeding up now at a diminished rate. So the rate at which it speeds up is decreasing, but the object is still speeding up. And since it's still speeding up, the drag force is going to continue to get larger and larger and larger. And so you can imagine now we're at a later point. And maybe now we've got gravity acting down. mg is still 20 newtons. And maybe it's sped up now to the point where the drag force is also equal to 20 newtons. So it's going so fast that the drag force is equal to the force of gravity. And what we can see now, I probably don't need to do the calculation out, the net force is 0. And if the net force is 0, that means the acceleration is 0. Well, what does this mean that the acceleration is 0? Well, that means it will no longer speed up. It will now fall at constant speed. Right? We've never accounted for this yet in this course. In this course, we've said if you drop an object, it accelerates at 9.8 meters per second squared forever. But that's because we've been ignoring air resistance. In the real world, when you drop an object, it speeds up for a little while, and then eventually it reaches a point where it no longer speeds up and it falls at constant speed. And this constant speed is known as the terminal speed, or terminal velocity. It is the final velocity. Terminal means final, end. It is the final velocity an object reaches when you drop it in the presence of air. It will speed up for a period of time and then stop speeding up, and that maximum velocity, that Vmax that the falling object reaches, is called terminal velocity. That's all I really have to say about this topic. You'll have a short problem set where you'll do some practice with this.